So today's lesson is one of the thermodynamic calculations. We call it thermochemistry in chemistry. We're going to be looking at how heat is exchanged, or how much heat is exchanged, when there is a temperature change. Alright, so we're looking at thermochemistry. Thermo just means heat. Chemistry is the study of matter and its interactions. It's also called in physics and engineering thermodynamics. Dynamics can be thought of as moving things around. So thermodynamics is about moving heat around. Okay? Now heat is a form of energy. Okay? And you can't measure heat directly. There's no device you can stick in something and measure the heat. It must be measured indirectly. By moving it around. Now, there's a common misconception among students in general, not just high school students, but particularly I find in high school. They think that heat and temperature are the same thing. But they are not the same thing. Okay? Heat is not temperature. Temperature is a relative measure of the amount of heat stored in a substance. Oops, how to spell relative, right?
Did you go to the headphones in there?
No, I did not.
Are you still recording this?
Yes.
I'm sorry.
So temperature is a relative measure of the amount of stored heat. Now there's heat everywhere. I know you guys think if you went to Antarctica there'd be no heat there. There is heat there. Okay? Heat exists everywhere, even in the coldest parts of space. Alright? And what you do to use heat energy is move it around. It doesn't do any good just to sit in one place. When you move it around, then you can get some work done with it sometimes. Okay? Let's talk about this temperature being stored heat for a minute. You can't feel temperature. I was expecting Maya to say, "What? Are you kidding, Mr. Tedder?" You can't feel temperature. Okay? You feel the exchange of heat. Okay? And here's a way that you can test that. We're kind of getting to the end of the summer now, and it was pretty hot out yesterday. If you were outside a lot yesterday, okay, if you were outside a lot yesterday and you walked into your house, how did it feel to you?
Cooler.
It felt cooler. Okay? Let's say that your temperature in your house was 72 degrees Fahrenheit. I know we don't use Fahrenheit in here, so I'll let you know that 72 degrees Fahrenheit is about 21, 22 degrees C. Okay? In the hardest, the coldest parts of the winter, when it's like freezing outside, and you've been out there for a while, you walk inside, and it's 72 degrees, or more correctly, 21, 22 degrees C. How does it feel then? Does it still feel cool?
No, it feels warm.
Feels warm. Same temperature, but it feels different to you, doesn't it? That's because you're not feeling the temperature, you're feeling the heat energy going into your body or out of your body. In the summertime, where you're going in and you're hot, you're feeling the heat energy leaving your body. It feels to you cooler. In the wintertime, you're feeling the heat entering your body because you've been outside where it's cold and all your blood vessels are constricted and stuff, and you're feeling the heat energy enter your body. It feels warm. Okay? So you don't feel temperature. In fact, you can be fooled about the temperature because of what your experience is immediately prior to whatever you're walking into. Yes?
What, so say like you're in the middle of like Antarctica or something. Where is the heat there? Like you said it was heat everywhere.
Okay, there's always heat there. It's just the amount of heat we're talking about. Okay? There's always heat. Doesn't matter whether it's Antarctica, the deepest parts of space, there's heat there, but there's just not as much there as there is where we are right now. Okay? All right. So let's talk about how to do some calculations with heat. And that's what we're going to be doing here in this first day of Unit 10. We're going to be looking at heat energy. So let's look at the symbol we're going to use for heat energy. 10. The heat energy symbol is Q. Sometimes you see it written as a capital Q. I like to use the lowercase q. That's how you see it written most of the time. And that symbol then is the symbol for heat energy. Okay? Now we measure heat energy in units of joules. Notice I wrote this with a capital J. That's because this unit of heat energy is named for a person. So whenever we're using a unit symbol, most of the time we use, up to now, you probably use mostly lowercase letters. When we're talking about grams, we use lowercase g. Okay, when we're talking about milliliters, somebody asked me about that a minute ago, we use a lowercase m. Although I ask you to use a capital L, I'll talk about that in a minute. But when we name a unit of measurement for someone who's famous in the world of physics or chemistry for whatever they have been working on, if we name a unit of measurement after them, then we're going to capitalize it. So the symbol for joules then is a capital J, not a lowercase j. Okay? Now here's why I ask you to use a capital L for liters instead of a lowercase l. Let me put this on a separate sheet of paper here for a minute, okay? Here's the question. What is that? Are you sure it's a 1? Is it a lowercase l? Are you sure?
You don't know.
You don't know. It could be a capital I. So it's confusing. So we don't know what it is when you write that. To avoid confusion, I ask you to write liters with a capital L. So if we're writing milliliters, it's a lowercase m but a capital L. That makes sense? Okay. Now, back to our lists of things we're going to talk about here for our study of thermochemistry. While we're on that subject, let's be careful about a couple things. Sometimes the same symbol is used for a dimension of measurement and for a unit of measurement. Okay? So, for instance, m, if I were to write the letter m after a number, that would mean that is a certain number of meters. But if it's a dimension of measurement, then this stands for mass. Okay? Now you've got to be careful about that. So when you see an equation, a general equation, those are symbols for dimensions of measurement. When you put in numbers for something you've measured or calculated, then you put in the units of measurement. That's a different thing. The unit of mass we most often use in chemistry is the gram. We might be using kilograms. Okay, might be using micrograms. Yes.
But I'm confused on how you said, how do you know if it's m for mass or m for unit?
Okay, if it's an equation, a general equation for something, those are symbols for a dimension of measurement. If you put the symbol after a number, then you're indicating that that is a unit of measurement. So if I have 12m, that's 12 meters. But if I have just the letter m in an equation, that means mass. Okay? All right, the symbol that we use for temperature is a capital T. Now this isn't named after anybody, but lowercase t is what we use for time. So we just differentiate between temperature and time by using capital T or lowercase t, okay? So this is temperature. As I hinted about a while ago, we don't use Fahrenheit in here, okay? We use degrees C, Celsius or centigrade, or Kelvin. Why? Because Fahrenheit doesn't work as easily with the calculations we do. Conversions are a lot easier if you're using degrees C or if you're using Kelvin. When we get to gas laws, you'll be required to use Kelvin. And there are degrees C and degrees Fahrenheit. There are no degrees Kelvin. It's just Kelvin. Okay? All right. Delta. I know that looks like a triangle, but that's the Greek letter delta. Okay? And it means change. All right? And then a capital C. Now, capital C is the symbol we use for heat capacity. Capacity of heat, C. Okay? The reason we have a P here is because it's indicating constant pressure. You don't need to know that in here because we don't get into changes in pressure for which we use this capacity of heat or heat capacity. Everything's going to stay at atmospheric pressure, the pressure in the room, so there's no reason to worry about whether you change pressure, but generally speaking, we always write it, when the pressure stays constant, then we use the heat capacity for constant pressure. Heat capacity or capacity of heat, or it's sometimes called specific heat, okay? Specific heat, although it's slightly different. When I say specific heat, I'm meaning, in this class at least, I'm talking about heat capacity. Now, something about heat capacity that's important for you to know. All substances have at least 3 different heat capacities. Okay, and that's for solid, liquid, and gas forms of the same substance. So water, for example, we use water's heat capacity a lot. Water has a heat capacity for ice. It has a different heat capacity for liquid water, and it has a third heat capacity for steam or gaseous water. Okay? Specific heat is a ratio that shows how well a substance stores or releases heat energy. And I should be clear and say substance or material, because to a chemist the word substance is very specific. We'll get to that a little later. Trying to spell releases right now. Gracious. Okay, so I'm showing you the example of how you're supposed to handle mistakes in your lab logbook. I drew a single line through the mistake. Of course, I'm going to white it out just to make it easier to read for everybody, but that's how you should do it in a lab logbook. If you make a mistake, you don't white it out, you don't scratch it out, you just draw a single line through the error. Okay? Yeah. Yes. All right, now. So, all of these are going to be used in one of our 2 equations that show how we that are going to be used in this class at least for figuring out how heat is exchanged and how we calculate it, okay? All right, so here's the equation I want you to know. Q, heat energy, is equal to mass times the specific heat times the change in temperature. Now you have to know which specific heat to use. Remember that, okay? For at least in the beginning, I'm going to give you these, but then later on, you'll have to kind of figure out which specific heat to choose at a given temperature. Water's freezing temperature is 0 degrees C. Water's boiling temperature is 100 degrees C. So if you're between 0 and 100, you're going to use the specific heat for liquid water. If you're below 0, you're going to use the specific heat for frozen water, which we commonly call ice. And if you're using water at above 100 degrees, then you're going to use the specific heat for steam or gaseous water. Okay? So how do we calculate delta T, the change in temperature? Well, that's a sort of a separate equation. We could include it in this equation. I like to break it out to be clear about it. So delta T is always final temperature minus initial temperature or beginning temperature. Okay? And anytime there's a calculation of change, you're always going to start with final and subtract initial. Okay? Anytime you're calculating a change, it's always going to be the final, whatever it is you're looking to change of, minus the initial, whatever it is you're measuring the change of. Okay? In this case, it's going to be temperature, but in the future, it might be something else. Okay? Let's talk about, before we solve the first problem, the steps I want you to use, because you're going to use these same steps later in the semester for gas laws as well. And it'll help you to get to make yourself familiar with the process, okay? So when you're solving these problems, in order to get full credit for the work, the first thing you're going to do, step 1, you must write the equation needed with no values plugged in. Okay, that's the first step. So if we're solving a problem that has to do with change in heat for a substance, then we're going to plug in this equation and that equation. That's the one we're going to need here. Okay? Now, anytime you write those down, you have to have the units of measurement in there. Okay? Because in step 2, you're going to, well, step 2 is to plug in, and step 3 is where you cancel. In step 2, you're going to plug in values, and you must include the units of measurement. Okay? And step 3 then is to cancel the units. If there were chemical species, you would also include those. There won't be in these calculations, but if there are units, if there are species involved here, you'd include those. You're going to cancel the units, check, and solve. Okay? Okay, now it's not one of the steps, but don't forget to round. All right. So let's do a problem here. The heat capacity or specific heat of liquid water is 4.18 joules per degrees C per gram. How much heat energy is needed to heat a 32.5 gram sample of water from 12.0 degrees C to 38.4 degrees C. Okay. Yes.
Is that a 1 in front of the C? Or, yeah, is that a 1 or is that
Here,
yeah. What is all of that?
4.18 joules per degree C per gram.
Oh,
That's degree C. Okay. Sometimes you're going to see this written, particularly on the internet, because fractions are kind of hard to do on the internet. You'll see this written like this. Tell you what, let me do it like this. 4.18 joules degrees C -1 grams -1. Okay. When you have a number written like this, the -1 in that superscript position here means that goes in the bottom of the fraction. Okay? Like, 10 to the -1 is a tenth. That makes sense? It's like you put 1 over 10 in a fraction. Okay? All right. So let's use our three-step process and solve the problem. Okay? First thing we want to do is to write the equation needed. Well, let's see. We have heat energy needed, so we know that's probably going to be Q. We know the mass, and we can figure out the change in temperature. So the equation we're going to need here is Q equals mass times the specific heat times the change in temperature. Now we've got to calculate change in temperature, so we're going to need that equation. Change in temperature is temperature final, which you could write as T sub F, minus temperature initial. Okay. Now we're ready to plug in the numbers. Okay. Q is equal to the mass. The mass is 32.5 grams. 32.5. Got to make sure you have your units of measurement.
Can you put the light on it?
Specific heat is 4.18 joules per degree C per gram. And we've got to calculate the change in temperature to plug that in. And I've asked you, whenever you're doing addition and subtraction, that you do that vertically. Meaning, if I'm going to start with the final temperature, I'm going to put in 38.4 degrees C minus 12.0 degrees C and when I subtract I get 26.4 degrees C, and that's the change in temperature. So now I've got a number to plug in here. No, depends on what the problem is. Problem can be different. You just have to interpret what the problem is. If you're going to add or subtract, okay, then you're going to put your numbers vertically like this. So if there's an empty slot over here, you know to round off that digit. In this case, there's no empty slots. There's no reason to round off.
So I'm saying, are we going to always subtract? Or like, what we add just to find that number?
Well, it depends. Again, it depends. Okay? Delta T is final minus initial. Okay? All right. In order to do the dimensional analysis, it's a good idea to put these numbers here over 1, this one and this one. Okay? Now you can see where to cancel. That makes sense? What am I going to cancel? The grams are going to cancel. The degrees Celsius is going to cancel, leaving us with joules, and joules measures heat. So the beauty of dimensional analysis is I know I've set the problem up right because I have the units left that I need for this problem. That makes sense? That's why I say cancel and check. You can check your units to see if it matches what you're seeking here. All right? And now we're ready to solve the problem. Everybody have their calculator? Need your calculator so you can practice these things. The more you use your calculator, the faster, more smoothly your calculator operations are going to be on the test where you really need it. Okay? And you're not confused about the calculator when you're also confused about other things on the test. It helps you to, get right to the problem without having to worry about it. So you need a calculator every day so that you can practice this stuff every day. Okay? That's correct. So the question she asked was, do we multiply everything? Yes. Everything's on the top of the fraction. Okay, let's go back and look at that. Everything's on the top here. You divide by anything on the bottom, but we only have ones at the bottom, and divided by 1 just gives you the same answer you started with. So is this the answer you guys got?
Yes.
Okay. Okay, so what units do I still have left? Joules. I need to make sure I put joules here. And don't forget to round. Okay, I put that part of the list on the bottom of the list down here. Don't forget to round. How many digits do I need for the final answer? 3 digits. We're going to look at the measured and or calculated numbers. This is a measured number. This is a calculated number. We actually calculated this one. So of those 3 numbers, the one with the least digits is the one that tells us how many digits we want for our final answer. So if I've got 3 digits in all of these, I need 3 digits here. Therefore, I count 1, 2, 3 and underline everything else. Okay? And now I've got to round it off to 3 digits. So, is that the right answer? I see a few people saying yeah, but most of you got it now, okay? 300 something is not even in the same ballpark as 3,000 something, okay? This is an order of magnitude smaller than this, all right? So this is not the correct answer. What we have to do is anytime we're getting rid of a number in the ones place, like we're getting rid of a number, this 6 here is in the ones place, we have to write the answer in scientific notation, in order to get a correct final answer. So we're going to move the decimal place to the slot between the first and second significant digits right there. And we're going to write 3.59. Since we moved the decimal place 3 places, that's an order of magnitude of 3. So we're going to say times 10 to the third. That's what the order of magnitude means right there. It's what that exponent is. And the units of measurement is joules. Does that make sense? All right, let's do another problem. I'm going to let you guys work on it either by yourself or with a learning partner, somebody near you you don't mind working with. I encourage you to work with other people. The specific heat of ice, solid water, is 2.05 joules per degree C per gram. Notice the specific heat here for ice, solid water, is different than that of liquid water we had earlier. Okay, I told you that would be the case. So now this is an example so you can see that.
And can you look this up on the internet and I'm like, you know what I'm saying, like, and I'm looking at it.
Hold on. So the question is, if a sample of ice in your freezer has a mass of 2.47 grams and a temperature of negative 5.00 degrees C, and it's cooled to negative 15.00 degrees C, how much heat energy is removed? So we're going to pause this video, and if you're watching this, solve the problem. And once you've solved the problem, check your work by what I do next. All right. Let's take a look at the solution of the problem then. So we have a heat energy problem. Okay, we have a change in temperature and we have mass of a substance. Okay, so the equation we're going to need is Q equals mass times the heat capacity times the change in temperature. We're going to have to calculate change in temperature. So delta T is equal to temperature final minus temperature initial. And we're going to add or subtract these vertically to keep up with the significant digits. So our starting temperature, the initial temperature is this, and this is the final temperature here. Okay? So the final temperature is negative 15.00 degrees C. Our final temperature I'm sorry, that's not right. It's starting out with 5, isn't it? And going down to 15. Okay? Let me take the 1 out of this. All right?
Wait, no, that's right, because the final is 15.
Yes. Oh, you're right. Okay, you got it. I don't want to confuse you. I'm sorry. You're right. Here we go. All right, we're starting out with 15 because that's the final temperature. We're going to subtract the -5. And when you subtract -5, it's like adding that. That makes sense? Okay? When you subtract a negative number, it's like adding it. And so what you end up with a -10.00 degrees C. You can put in your calculator to do it for you. But just so you know, that's what happens. Okay, that's okay. All right? So now we can plug that number in here along with the other numbers we have. And the mass is 2.47 grams. The specific heat for ice or frozen water is 2.05 joules per degree C per gram. And our change in temperature is a -10.00 degrees C. And we're going to put all these over 1 so we can see how to cancel. The grams are going to cancel. The degrees C are going to cancel. We're left with joules. Joules measures Q. That's what heat energy is. Okay, so we're ready to plug it in the calculator. We get a negative then 50.635 joules. Okay, so that's the heat energy removed, which is what the question asks. I'm just kind of heading your minds in the right direction. Anytime temperature goes down, you're removing energy. Anytime temperature goes up, you're adding energy. Just like we used the example earlier, when in the summertime you're hot, you go inside, heat energy leaves you. You feel cooler. Does that make sense? And it's wintertime, you're cold outside, you go inside, you feel warmer. The temperature inside is the same, but it feels warm because heat energy is now going from the room into your body. And that's what we're talking about here. Heat energy is leaving the system, or what we're interested in here. We need to have the right number of significant digits. We have 3 digits in this measured number, 3 digits in this calculated number, 4 significant digits in this calculated number. So of all the measured and calculated numbers, these 2 have the least digits. We want our final answer to have that same number of digits, 1, 2, 3, underline the 3, 5, draw an arrow to show that we're rounding off, and our final answer is negative 50.6 joules. Got it?
Yeah.
I mean, I don't think the test is going to be any harder, but, some people say it is. But, who knows? I mean, I just think it's all the same stuff. It is like this. Okay? Well, usually, trust me, in college you're going to be doing a lot more complex work than this. Okay? All right, now, any questions about how to do this? All right, then.